Hello, dear students. Welcome to the channel and welcome back to this amazing playlist in which we are discussing about different types of faults which can take place in power systems, like symmetrical faults and unsymmetrical faults. So, in the beginning part of the playlist, we have discussed about symmetrical faults. Then we have discussed about symmetrical components, in which we have discussed about positive sequence network, negative sequence network, and zeroth sequence network or zeroth sequence components. And from previous lecture, we have started discussing about unsymmetrical fault on power systems, and in that initially we have discussed about what different kind of faults which can take place in my power system. So we divided unsymmetrical faults in two categories called shunt and series type of faults, and later on we saw the shunt type faults in detail, in which we saw the single load single line to ground fault, line to line fault, and double line to ground fault. All three of them were for synchronous generator, and today we are going to see the same thing: single line to ground fault, line to line fault, and double line to ground fault for my power system. So if you have seen the previous video, this will be a cakewalk for you. But if you haven't seen the previous video, and if you are interested to know about the single line to ground fault, line to line fault, and double line to ground fault for my uh, synchronous generator or unloaded alternator, then the link for previous lecture will be flashing on the top right hand side corner of your screen in the I button, so you can click on it and see the video. So now that out of the line, let's start with today's class, in which we are starting with unsymmetrical faults on power system. So all the faults we have discussed till now, and till now I mean till previous lecture, these faults are easily analyzed by using my Thevenin's theorem. And this Thevenin's theorem is used to determine the changes in current and voltages of my linear network because of any addition of impedances between either two nodes, right? So see the first figure which has been drawn here, figures 6.5.1. In that, what we have done, we took two generators on either sides, and then we are having a my bus bar, and we are connecting it with delta to star, with star grounded, and then star to delta with delta grounded. So that's my power system. And the next one, this figure, in this one you can see the representation of Thevenin's theorem for my positive sequence, negative sequence, and zero sequence network. In first one is for positive, second one is for negative, and third one is for zeroth. So basically, positive and negative are equal, except in negative there is no EMF source, uh, not EMF source present in my circuit, because remember what were the values of uh, VA1, VA2, and VA0 we have derived. So based on that, we have formed these circuits, and because of that, my negative sequence network is not having any circuits, right? So the Thevenin's equivalent of positive sequence network is obtained from the positive sequence network of my power system, and same you can do for the negative and zeroth as well. And again, about the voltage source, so the Thevenin's voltage source is the pre-fault voltage at my fault point, and the equivalent impedance Z1 EG can be the impedance which can be seen from the fault point as well. So here this one is my fault point, and the impedance corresponding to that is Z1 EG, as you can see here. Same thing you want to see for my negative sequence component, then it will be Z2 EG. Fault point is occurring here, so you can find the similar thing for negative sequence component and zeroth sequence component as well. For zeroth we are having Z3 EG. Alright, sorry, Z0 EG. So this Thevenin's voltage source is the pre-fault voltage at my fault point, and this equivalent impedance Z1 EG is the impedance seen from my fault point again. Now this positive sequence impedance of my synchronous generator, which we have discussed about in previous lecture, it will be dependent on the state of my machine, right? And we know there are three states of my machine. First state can be sub transient state. It will last for very less amount of time, but uh, eventually uh, the value of transient in this state will be too high. Then we are having a transient state which will last a little bit longer than subtransient but less than steady state, and third one will be the steady state, which will be the longest period. And this Thevenin's equivalent for negative and zeroth can also be obtained from the negative and zeroth sequence component of my power system. And a little small notice, small detail I want you to notice is this one. For zeroth sequence component, these two are short circuited here. So I want you to tell me what can be the reason for this. We have discussed about hint of this in previous class. So if you have seen previous class, I think it would be easy for you to grasp it. So please mention in the comment section below what can be the reason for it. So now as system is balanced, there will be no negative and zero sequence current flowing through my system. And this situation is I'm talking about before the fault has been occurred, when the system was balanced. So at that time there will be no flow of negative and zero sequence current, there will be only positive sequence current flowing through my circuit. And when such thing happens, then the per fault negative and zero sequence voltage at the fault point will be zero, because it's not taking place in the first place, so it will be zero. And the impedance Z1 EG and Z2 EG are Thevenin's equivalent impedance of my not Z1 EG, I'm sorry, Z2 EG and Z0 EG are Thevenin's equivalent impedance for negative and zero sequence network, which can be seen from fault, just like Z1 EG, which was for positive sequence. So speaking of positive sequence, in positive sequence network, the current throughout the system due to the fault that can be added to my load current before your fault gets obtained, the total positive sequence current will be obtained during the fault. So in positive sequence network, the current throughout my system due to the fault can be added to the load current before the fault to obtain total positive sequence current during the fault. And because of that, the net fault current will be the fault current considering the system under no load condition, and then you will add the load current which superimposed over the fault current. So by that way you can find it. Now moving towards the next topic which I wanted to discuss, the single line to ground fault on my power system. So basically the faults which will be occurring in line to ground, line to line, or double line to ground, all three type of faults will be very similar to the same faults which occurred for the synchronous generator, which we discussed in previous class. So here I will be moving a little faster so that we can cover more ground. So consider the first power system. As you can see in this picture, we are having three phases A, B, and C. And C, there is a line to ground fault which is occurring at this point of uh, A phase. We are calling this point F, and the fault impedance is ZF. Okay, so this line is getting grounded with ZF impedance. So when such thing happen, what will be the value of the currents and voltages? Okay, so when one phase among three phases will get grounded and other two phases will remain as it is, at that time what will happen, the current which will be flowing through my other two phases will become zero. So IB and IC both will become zero, and the voltage across this phase VA will be the multiplication of current flowing through this line, which will be VA, current flowing through this fault VA, and the impedance ZF. Right. Now similarly what we did for synchronous generator, we will do the same thing here. We will try to find the positive, negative, and zero sequence for current, and we can use the same formula which we did previously. Ia1, Ia2, Ia0 equals to 1 by 3 A into I matrix. Okay, A matrix is again, this is the A matrix, 1 alpha alpha square, 1 alpha square alpha, 1 1 1, and I matrix will be Ia 0 0 because IB and IC are 0. So when you do the math, you will find out that Ia1, Ia2, and Ia0 will be equal, and all three of them will be one third into Ia, which means my Ia is getting divided uh, in three parts. Not exactly getting divided, but yeah, you can say it is getting divided in three parts of Ia1, Ia2, and Ia0, positive, negative, and zero sequence. And about the voltage value, the voltage across the phase which is on which the fault has occurred, we have given that voltage VA is equals to ZF into IA. So if you want to express it in terms of symmetrical components, because now you know what is the value of IA in terms of symmetrical components, so you can represent it this way: VA1 plus VA2 plus VA3, VA0 is equals to, because VA is basically the sum of VA1 plus VA2 plus VA0, so it will be equal to ZF into IA. Now you know what is the value of IA, which is equals to 3 into IA1, so you will simply write 3 ZF into IA1. Alright, so what does these two equations tell us? The last two equations which we just derived, that my symmetrical current, symmetrical components of positive, negative, and zero sequence for my fault current IA are equally distributed, and the second one is telling us the voltage values: VA1 plus VA2 plus VA0 is equals to 3 ZF into IA1. So these two equations indicate that all the sequence currents are equal, and sum of the sequence voltages, right, which are equal to 3 ZF into IA1. And these equations, what do they suggest to us? That they suggest that all the sequence networks should be connected in series through the impedance 3 into ZF. So we will do exactly that, and when we do that, my my circuit will look like will look something like this. Here I'm having the positive sequence network VA1, negative sequence component VA2, and zero sequence component VA0. And here I'm having IA1, IA2, and IA3, and we are connecting it with IA1 into ZF, 3 ZF, right? And what will be the value of IA1? So IA1 will be 3 into IA1 will be 1 by 3rd into IA. IA is basically my fault current. So again we did based on this circuit, we derived the formula for IA1. So you can do that too. So by deriving this formula, you will come across this formula IA1 is equals to E0 or EA divided by Z1 plus Z2 plus Z0 plus 3 into ZF. Right, so that will be the formula for your fault current, the positive sequence of fault current. And if you want to find the fault current, then this value will become 3 into IA1. Right, so your if you want to find the total fault current, you have to multiply your IA1 with 3. We can also draw the Thevenin's equivalent circuit for my LG fault. So same as we did for unsymmetrical, same as we did for unloaded generator, unloaded synchronous generator, we will do the same thing. You will have your EA here. Here we are having all three impedance components, Z1, Z2 and Z0. Now IA0, IA1 and IA2 will have same values, and here I'm having 3ZF. Right, we have connected them in series, as you can see, based on the equations which we derived. And based on this circuit, Thevenin's equivalent circuit of my LG fault, we can also find the voltages. Right, we can also find the value of VB. Right, and how can you find it? So again, you can do the same trick again, the same thing we did for a synchronous generator. So by doing that, your formula for VB will look something like this. VB is equals to alpha square VA1 plus alpha VA2 plus VA0. And you know what are the values of VA1, VA2 and VA3 from previous lecture. So you will substitute those values and you will be able to find the value of VB based on that. And in that you can also substitute the value of IA. So the final formula for VB will look something like this. I'm not going to pronounce it because it's kind of a tongue twister. I don't even want to make an effort, but know that this is the formula. Now let's move forward to line fault. So this one, from your from the left hand side of the screen, you can see the line to line fault. Two lines, phase B and phase C, are short circuited, and the fault impedance between both of them is ZF. There is nothing wrong with phase A, but whenever there is a short circuit between two lines, then the current from the third line will become 0, and the current in these two lines will be equal but will be flowing in the opposite direction. Both of them are basically short. And the potential difference between these two lines, can you tell me what will be the value of potential difference between these two lines? Basically it will be equal to the current flowing through this line or this line, doesn't matter, IB into this fault impedance ZF. Right, now we will do the same thing again. We will try to find the symmetrical components for current. And we again, till now, I bet you must have remembered the formula. So formula for symmetrical component of current will be 1 by 3 A into matrix I. Now you already know what is the value of matrix A: 1 alpha alpha square, 1 alpha square alpha, 1 1 1. And you will be multiplying your your current vector, and your current vector, in your current vector, value of IA will be 0. So 0 into 0, then IB, and then IC. But you know what is the value of IC? It is equals to minus IB, so we will be mentioning minus IB. And when you calculate, you will find the values of IA1, IA2 and IA0. Value of IA1 and IA2 will be almost identical, but uh, in opposite direction, which means the signs will be complementary. So if IA1 is positive, then IA2 will be negative, and zero sequence current will be 0 here. Right, zero sequence current will be 0 because the current flowing through one of my phases is 0. Now you can similarly, now you have value of IA1, IA2 and IA0. Same ways you can find the value of VA1, VA2 and VA0 as well. So symmetrical component of voltages will be there for you. And again, you know what are the value of voltages. This will be va, this will be vb, but the value of vc will be equal to, because we remember we derived the potential difference between these two lines, which means vb minus vc will be ib into zf. So if I want to make vc subject, what will be the value? Vc is equals to vb minus ib zf. So we have written vb minus ib zf. Here you go. Now derive the formula for va1, va2 and va0. 1 into va plus alpha into vb plus alpha square into this term. Same way as you can derive for va2, 1 into va alpha square plus into vb alpha into this term. And same way as you can derive for va0 as well. So when we derive the formula for all three of them, you will find out that va1 and va2, you can take the subtraction of them. And when we take the subtraction of va1 and va2, positive and negative sequence current, what you will find? The answer will be 1 by 3 alpha minus alpha square zf into ib. By the way, do you think you have seen this thing, all these things somewhere, and like the feeling that you are getting deja vu, that you have already seen it, you are repeating the same thing? If you are getting it, that means you are following this lecture series very continuously, and this part is something, it holds very much resemblance with what we did in previous class for synchronous generator. It is the same formula, same derivation, we did it for the synchronous generator as well, and same thing will happen for power system as well. So same ways, you will be taking the subtraction of va1 and va2, you will be getting this value. And again, the value of alpha minus alpha square, I've told you in the last class as well, j into root 3. So you will put j into root 3 here. And after that, you can find the value of ib. So to find the value of ib, you have to take the inverse of matrix a. So you will take inverse of matrix a into the symmetrical components. And again, doing the multiplication, you can find the value of ib, which will be ia1 into alpha square minus alpha. So now alpha, if alpha minus alpha square's value was j into root 3, then the alpha square minus alpha will be minus j into root 3. And from that, you can find the value of ib, which will be minus j into root 3 into ia. Now what you will do, you will simply replace the value of ib in the equation of voltages, and by doing that, you will be able to find the voltage difference between positive sequence component and negative sequence component, which is nothing but zf into ia1. Okay, ignore this capital F, this is not frequency, this is this should have been a subscript, but I think this is a typo error. So instead of z underscore f, they have written z into f. Okay, it's a typo, so don't get confused. Now from these last two equations, uh, the equation for ib and the equation between equation of voltage between positive and negative sequence component, what does it suggest to us? That it tells us that a positive sequence network is connected in the parallel connection with my negative sequence network through the fault impedance if, as you can see, right? And as the zeroth sequence is basically 0, right? ia0 is the zeroth sequence and basically it is 0, so it will remain unconnected. So when you do so, here you are having positive sequence, here you are having negative sequence, you are connecting both of them in parallel. So here you are having the basic circuit sequence network connection for line to line fault, right? Here's va1, here's va2, here's the ia1, here's ia2, and here's the zf. And same ways, you can draw the same thing for Thevenin's equivalent circuit as well. And when you do so, you will have ea, you will have z1 and z2, both of them are parallel to each other, and you are having between them you are having zf, and here you are having ia1 and ia2. So from this Thevenin circuit, you can also find the value of current. So from this circuit, what will be the value of IA1? You can tell me. It will be the voltage source EA divided by Z1 plus Z2 plus ZF. Basically, all three of them in series. So it will be it. And from the previous equation, the equation of IB, this one, yeah, from this equation, you can find the value of IB simply substituting value of IA in here. So it will be j into minus j into root 3 into the whole value of IA, which will be this. And now that you have your value of IB, same ways from IA1, VA1 and VA2, you can also calculate these values, and from this voltages at fault point you can also calculate. So that was your line to line fault. Now let's move forward and see what is the line to ground fault or double line to ground fault. So basically in this one, what is happening, two different circuits, two different phases are getting short circuit and then getting grounded at the same time, and the fault impedance through these two phases will be ZF again. So you can see the double line to ground fault illustration in the uh, picture here. So the fault is occurring on line B and C through the fault impedance ZF. And when such thing happens, always remember the positive, negative and zero sequence components sum will be still zero, but the current flowing through the A phase will become zero. Why? Because remember in the last case what did I told you, that whenever short circuit happens between two phases, the current through the first phase will become zero. So same thing is happening here. IA will be zero. IA1 plus IA2 plus IA0 will be zero. The logic has been explained by me earlier. And VB will be same as VC because both of them are short circuited. And what will be the value? Because see, we are having ZF as impedance here, and the current coming through here is IB plus IC, so it will be ZF into IB plus IC. And previously we have also derived what is the value of VC, so it was 3 ZF into IA0 as we derived previously. So on the symmetrical components of voltages we will be try to find, and now then we know what is the formula. VA1 VA2 VA3 is equals to 1 by 3 matrix A into matrix V, and you basically have to substitute the values. You know the values of matrix A. For matrix V, you know a value of VA, you know VB, but VB and VC are equal because these two phases are short circuited. So instead of VC you can also write VB, and when you find the value of VA1 VA2, you will know that the value of VA1 and VA2 will be same, right? See, VA1 will be VA plus alpha into VB plus alpha square into VB, and what will be the VA2? It will be VA plus alpha square into VB plus alpha into VB. So basically both of them are equal, and uh, the value of VA0 will be 1 into VA plus 1 into VB plus 1 into VB, which means 1/3 will remain as it is, VA plus 2 VB. So you can see the formula here. And now as we have same values of IA1 and IA2, you can instead of IA1 and IA2 you can write either one of them as well. So now what we will do, we will take this subtraction of my either positive or negative sequence voltage component, because both of them are equal, and my zeroth sequence voltage component. And by doing so, the value we will be finding will be VA0 minus VA1 is equals to 1/3 2 minus alpha square into VB, right? Basically you are taking subtraction of this term and this term, so 1/3 will remain as it is. Basically you will get it outside common. Your VA will get cancelled, so you will be left with 2 this 2 minus alpha minus alpha square into VB. And you know what is the value of VA0 minus VA1. So instead of that, you can also write 3 into ZF IA0. So if you want to find the value of VA0, then it will be VA, you can send this VA1 on the other side. So it will be VA1 plus 3 into ZF into IA0. So now same way as the previous three equations, this equation for VA0, then the initial equation which told us that symmetrical components are equally distributed, so sum of them are sum of all three of them is 0. And the other equation, the equation for my VA1, these three equations are indicating that the positive sequence and negative sequence networks are connected in the parallel connection, and this parallel combination is connected to the zero sequence network through the fault impedance ZF. So how can you represent it? So you can represent it via this circuit diagram. See, VA1 and VA2 are in parallel, right? And then this whole circuit is in parallel connection uh, through to zero sequence network through my fault impedance. So we are having zero sequence and fault impedance in series, and that is in parallel connection to my VA2. Based on that, you can also form the Thevenin's equivalent circuit diagram, and by doing that, you will be finding value of EA. You will be finding Z1 and Z2 zero then for positive sequence, sorry, negative and positive sequence in parallel, and they are connected with zero sequence in parallel, which is connected to my fault impedance in series. And based on this Thevenin circuit, you can find the value of IA1 basically by applying the KVL in the loops. And when you do so, you will find value of IA1 will be EA divided by the equivalent of Z1 plus Z2. Basically they are in series here, plus uh, basically in parallel with the equivalent of 3ZF and Z0. And the remaining circuits, the equivalents of first one and other one, let's call them Z dash and Z double dash. So Z dash and Z double dash will be in parallel, so we will be taking the parallel equation of them, and by doing that you will be finding the value of IA, which will look something like this. So these were your line to line, line to ground and double line to ground fault for power systems. We will keep this lecture till here, and next time we will be seeing we will be doing some analysis of unsymmetrical faults using bus bar impedance matrices. We are keeping this lecture till here. I will be seeing you in the next class. Till then, take care of yourselves, and thank you very much for listening. Goodbye for now.